Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are taking a deep dive into total internal reflection, a key concept from Unit 9, ray optics and optical instruments. We're going to make sure you understand this core idea clearly for your exams, and actually for understanding how a lot of the modern world works. So let's start with something you might have even seen yourself. Imagine you are at the bottom of a clear swimming pool on a still day. You look straight up and you can see the sky, no problem. But what if you look sideways, towards the surface, but at a really steep angle? Suddenly that surface, it isn't transparent anymore. It acts like a perfect mirror. You see reflections of the pool floor.
Wait, that is quite strange. Water's supposed to be transparent. Light should just go through it into the air. Why would it suddenly turn into a mirror?
Exactly. Why would it just stop letting light out? And now think about something even more dramatic.
Yeah.
A diamond. The brilliance of a diamond, that intense sparkle.
Yeah.
It's not just because it's polished well, it's because the diamond is basically designed to do this trick. It traps light inside, bouncing it around again and again before it finally shoots out to your eye.
So you're saying the diamond is using the same physics as the swimming pool surface when it becomes a mirror?
Absolutely. That ability to just spontaneously turn a clear boundary into a 100% perfect internal mirror. That is the mystery we are going to unlock today. It's called total internal reflection, or TIR. Okay, so let's unpack the core idea. Total internal reflection, it's a very specific thing that happens when light tries to go from a denser medium.
Denser meaning where light is slower, like in water or glass.
Yes, exactly. When it tries to go from a denser medium like water to a rarer medium like air where it can speed up. Now, we know from refraction that when light goes from slow to fast, it bends away from the normal line.
Right, it bends away.
So if the angle it hits the boundary with, the angle of incidence, if that angle is too large, too steep, light tries to bend so much that it can't. It physically cannot get out. It's forced to reflect completely back into the water it came from. It's trapped. To really get this, think of it like escape velocity. Imagine you're throwing a ball upwards from the Earth, which is our denser medium. Throw it slow, gravity pulls it back. That's a bit like normal reflection.
Okay.
Throw it fast enough, and it escapes. Now, there's a perfect speed, the escape velocity, where it just about makes it outright.
Yes, the exact speed needed to escape gravity's pull.
That exact speed is our critical angle, theta psi. At that angle, the light ray doesn't really escape. It just skims along the surface.
Yeah.
The angle of refraction is exactly 90 degrees. It's just hanging on.
And what if you throw it even faster? Or in this case, what if the light comes in at an angle even steeper than that critical angle?
That's it. That's when total internal reflection happens. Beyond that critical angle, light just cannot penetrate the rarer medium. It has to bounce back 100%.
So why does this happen? You mentioned Snell's law before. Does it just fail?
It is basically a mathematical failure of Snell's law, which is what makes it so interesting. Remember, Snell's law is n1 sine theta I equals n2 sine theta r.
Right.
Now, if you rearrange it to find the angle of refraction, you get sine theta r equals n1 over n2 times sine theta I. Since we are going from denser to rarer, n1 is bigger than n2. So that ratio n1, n2 is greater than 1.
Okay.
This means that as you increase your angle of incidence, theta I, the value for sine theta r, gets bigger and bigger very fast. But
That's a problem.
the sine of any angle can never be greater than 1. It's mathematically impossible.
So at some point, if the angle of incidence gets too big, the formula will ask for a sine value that doesn't exist, a value bigger than 1.
Exactly. The math breaks down. Nature cannot produce an angle whose sine is, say, 1.1. So what does it do? It says, okay, the path for refraction is closed. The only other option is a reflection. And because no light can get out, all of it must be reflected. Total reflection.
So the failure to find a valid angle for refraction is what forces the total reflection.
I see. That makes the denser to rarer condition make so much more sense now. It's the only way the math could break like that.
Precisely. It can never happen the other way around. That condition is non-negotiable. Okay, so let's get a final mental image. Picture a ray inside a glass block, hitting the glass air boundary. At a small angle, it escapes. As you make the angle steeper, the exiting ray bends more and more, getting closer to the surface.
Okay, I'm picturing it.
Then, you hit that perfect critical angle and boom, the exit path just shuts down. The boundary becomes a perfect mirror, and every single photon is reflected back inside.
Wow, okay, that's a powerful image.
So now that we have that picture, let's get formal. Let's see how the insert defines this critical point. Could you read that for us?
Yes, the insert document states, the critical angle of incidence IC for a ray incident from a denser to rarer medium is that angle for which the angle of refraction is 90 degrees. Perfect. That definition is the key for your exams. So let's just break the whole process down into 4 clear steps. Step 1, the setup. Light must start in a denser medium and head towards a rarer one. If not, TIR is impossible. End of story.
Got it. Denser to rarer.
Step 2, we start increasing the angle of incidence, theta I. We're making the ray hit the boundary at a steeper and steeper angle.
Okay.
Step 3, we reach the critical angle theta IA. At this exact point, the refracted ray skims the surface. The angle of refraction is exactly 90 degrees. This is the breaking point.
And the final step is, if we go even a tiny bit beyond that.
That's step 4. If your angle of incidence is even slightly greater than the critical angle, you get 100% total internal reflection. All the light bounces back.
Yeah.
Now, from that definition, from step 3, we can get a really simple formula. Since the angle of refraction is 90 degrees and sine of 90 is 1, Snell's law becomes very easy. It simplifies too. Sine of the critical angle, sin theta A equals n rarer divided by n denser. It's always the ratio of the smaller index over the larger one.
Okay, sin theta c is n rarer over n denser.
Let's do a quick example. Light goes from glass, where n is 1.5, to air, where n is 1.0.
So we would do sin theta c equals 1.0 divided by 1.5. That's about 0.667.
Correct. And if you take the inverse sine of that, you get a critical angle of about 41.8 degrees.
So for a ray inside that glass, if it hits the surface at any angle greater than 41.8 degrees, say at 50 degrees, it gets completely reflected back inside.
Exactly. And that simple principle, that's the key behind fiber optics, the reason our internet is so fast.
Because the light is trapped inside the glass fiber.
Yes. The fiber has a core and an outer layer called cladding. The core is denser, the cladding is slightly rarer. Light is sent down the core at a very steep angle, always greater than the critical angle.
So it just keeps bouncing off the inside walls perfectly without losing any signal.
Almost no signal loss. It's nearly perfect reflection thousands and thousands of times over kilometers of cable. It's also used in high-quality binoculars and periscopes using prisms instead of mirrors.
Without any silver coating that can get old and tarnish.
Absolutely. A prism using TIR is a better, more perfect mirror than any coated one. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSA.com. Now let's talk about 3 silent killers. 3 common mistakes that students make in exams on this topic. Misconception number 1, thinking TIR can happen at any boundary, like from air to glass. Why is that wrong?
Oh, because the first rule, it has to be denser to rarer. Going from air to glass is rarer to denser, so the light bends towards the normal. The angle can never reach 90 degrees.
Exactly. So the hook to remember is always check the direction first. Denser to rarer is a must.
Okay, misconception number 2. Students think that because the light can't escape, it just gets absorbed or disappears.
But the T stands for total. It means 100% of the light energy is reflected. Nothing is lost.
Perfect. The hook is total internal reflection means a perfect mirror. And the last one, thinking the critical angle is a fixed number, like it's always around 42 degrees.
But we saw in the formula it depends on the 2 materials on the ratio of their refractive indices. Right, so for diamond, which has a very high refractive index, what happens to the critical angle?
If n denser is very big, then the ratio n rarer over n denser becomes very small. So the critical angle for diamond must be very small.
Very small. It's about 24.4 degrees, and that's the secret to its sparkle. Light gets in easily, but it's very hard for it to get out. It's trapped inside, bouncing around many times before it escapes, creating that brilliance.
Okay, so I must remember that the critical angle is not fixed. It is specific to the 2 media and is smaller for materials with a very high refractive index, like diamond.
You've got it. The hook is high refractive index meets a small critical angle, making TIR easy. All right, let's lock this in with a few memory anchors. For the formula, remember this phrase: TIR equals total internal refraction fails. The failure of refraction gives you the formula, sin theta c equals n2n1, or rarer over denser. And a catchy phrase for the whole concept. Denser to rarer, steep angle, light gets trapped inside. The perfect mirror without a coating. You can even do a physical gesture. Hold one hand flat, that's the boundary. Take a finger from your other hand, the light ray. Bring it in at a steep angle. And when it hits your palm, just pivot and bounce it straight back. That's TIR. And the best association is the one we talked about, your internet. Every time you stream a movie, you're using total internal reflection. It's the invisible backbone of our digital world. Okay, to summarize this entire deep dive, let's list 3 essential points for your exams. First, TIR is the complete reflection of light back into a denser medium when it tries to enter a rarer medium. Second, the two conditions that are absolutely necessary are
Light must travel from denser to rarer, and the angle of incidence must be greater than the critical angle. And third, TIR is technologically critical. It's what allows optical fibers to transmit high-speed data across the globe with almost no loss of signal. To get maximum marks in 12 CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam.com, right?
Yes, that is right. ProfSam.com. Thank you for joining us for this deep dive into total internal reflection. All the best for your preparations.